Hello, grade 12s. Today we're going to continue with nomenclature of organic compounds. We're going to learn how to give names to molecules composed uniquely of carbon and hydrogen. So the longest continuous chain is the parent name. So you could have an example here. You'd say 1, 2, 3, 4, 5. There's 5 carbons in a row. That's pentane. But what if you had another carbon sticking off the middle here? It would still be called pentane because the longest continuous chain would still be 5. See, this one is 1, 2, 3, 4, 1, 2, 3, 4. You can't get any other scheme where you would get a longer chain. And remember, these molecules are floppy, so you always have to, just because it's drawn a certain way doesn't mean that's necessarily the longest chain. Sometimes you have to count through the serpentine to find the longest chain. So the longest chain in this case is 5, but at the third position there's a methane group. But the third group says that when you have a substituent, which is something stuck onto something else, you drop the ane ending and you add YL. So in this case this would be called, and of course you number it to say where it's located. So this would be called 3-methyl, because you drop the methane and add eel, so 3-methyl pentane. That's what you would call this, 3-methyl pentane. Okay, number the chain so that substituents have the lowest possible numbering. In this case, if you count from the left, it gets to 3. If you count from the right, it gets to 3, so it doesn't matter in that case. Number 3, name the substituents by dropping the ane suffix and replacing with YL. Fourth rule is when substituents are more than 1, list them alphabetically. And there's a simple reason for that. If you're trying to look up a particular chemical in a catalog of chemicals, they should be alphabetized so that you can find them easily. And we all should agree on how to alphabetize so that anybody who knows what the name of the chemical is can look for it if it's offered. The fifth rule is cyclic hydrocarbons have the prefix cyclo on them. So for example, 5 carbons in a ring are called cyclopentane. Let's look at some further examples of isomerism. Now, remember I told you yesterday that isomerism occurs when you have a certain formula, but that certain formula can have multiple possible geometries, of not only geometries, but of actual locations of where the different bonds are and how the carbons are connected. So let's look at some examples of isomers of common alkanes. So I'll give you a nice example. Question: draw and name, which will give us plenty of practice, all the isomers of C8H18. So a molecule with 8 carbons, saturated carbon and hydrogen substance. It's called a hydrocarbon. Let's do this logically so that we list off all the possibilities, and there are 18 possibilities. So the first one is, and the most logical one is, to have them all in a single line. 1, 2, 3, 4, 5, 6, 7, 8. This is called octane. Sometimes you'll see that they put an N in front of it for normal, but that's not really necessary. If you just say octane without any specification, most people will assume you're dealing with a normal octane. Although in this particular case, because octane, the way we define it in the fuel industry is actually isooctane, it's not normal octane, but let's not split hairs. Second possibility, still has 8 carbons, but 7 of them are in the longest possible line, 1, 2, 3, 4, 5, 6, 7, but then we take the 8th one and we stick it on the second carbon. So again, you always try to number it so that you get the lowest number on the substituent. This is a substituent, and if you number from the left, it gets to 2. So this would be called 2 it's a methane group because it's only one carbon, but because it's a substituent, you drop the ane suffix and you replace it with eel. So you say 2-methyl, and the longest chain is 7, so it's called heptane. So 2-methylheptane. Third possibility, let's move that methyl group all the way down the line and get all the different possibilities. So we're going to have 1, 2, 3, 4, 5, 6, 7, and at the third position we put the methyl group, so that's going to be called 3-methylheptane. And these are all actual chemicals that exist. They have specific melting point, boiling point, and density, probably very similar, but with enough differences that you could probably separate them through distillation, or perhaps through, if a greater separation is needed, they would actually do something called gas chromatography or even liquid chromatography. Why you would want to separate these to that level that's another story. 4. Let's move that methyl group down the line. 1, 2, 3, 4, 5, 6, 7. Now we'll put it at the fourth position, so that's going to be called 4-methylheptane. Now you might be tempted to move it to the fifth position, but that would not be 5-methylheptane, because remember the rule where you say you have to get the lowest possible numbering, you would start counting from the other side and you would find out that it's actually 3-methylheptane, which you've already named. So let's move on to the next possibility. And that is, let's go down to a chain that is 6 long, 1, 2, 3, 4, 5, 6. But now we have 2 carbons to get rid of. So what we can do is put them both on the second position, in which case you would call it 2, 2, each one gets a number, dimethyl, because there's 2 of them, so you say di for 2, and then heptane. I could also separate the 2 methyl groups, put one here and one at the next position, so that would become 2, 3 dimethylheptane. Seventh possibility is right over here. 1, 2, 3, 4, 5, 6, and we'll say 2, 4 dimethylheptane. Then the eighth possibility, 1, 2, 3, 4, 5, 6, like that and like that, would give you 2, 5. Dimethylheptane. And is 2, 6 a possibility? Why is... No, because then it would become heptane. You can't put it at the 6th position, because then you'd go back to heptane. So that exhausts those possibilities. So now let's move this one. Let's move this methyl group to the 3rd position, and we can have them both at that position actually for the first possibility. So what did I do here? I'm just going to follow what I did on my paper. I have to make room, so I'm going to erase. So remember to do this logically, however your mind breaks it down. Exhaust all the possibilities, or else you'll miss something. So I was up to 2, 5. So my 9th isomer, as I listed them, 1, 2, 3, 4, 5, 6, I have 3, 4. 3, 4 dimethylhexane. I forgot to list 3, 3, but I did it after. So my 10th isomer is 3, 3 dimethylhexane. And why not 3, 5? 1, 2, 3, 4, 5. No, because that would make it 1, 2, 3, 4, 5. I think 3, 5 should work. Did I put it somewhere? 1, 2, 3, 4, 5. Yeah, I've neglected one. It's 3, 5. 1, 2, 3, 4, 5, 6. We have one at 3. So 1, 2, 3, 4, 5. Oh no, that's why. Okay, I get it now. Because this is actually 2, 4, which I have already listed. So 3, 5 is not a possibility. It's 2, 4. It would be a 2, 4. So number 11. 11th possibility is 1, 2, 3, 4, 5, 6, and at the third position, you put both carbons in one continuous chain. That would be an ethane, but because it's a substituent, we call it ethyl, and it's at the third position, so we say 3-ethyl hexane. Then you could have, that exhausts all the possibilities, because if you go to 4-ethyl hexane, it's still 3, right? 1, 2, 3 from the other side. It would be 1, 2, 3, 4, but you wouldn't call it 4-ethyl hexane, you'd call it 3-ethyl hexane, which we've already named, so it's just the same molecule flipped around. This is a little bit tricky, so you got to think carefully before you write an answer, because it's easy to create things that are actually identical until you've practiced. So that's the key, is the practice. 1, 2, 3, 4, 5. Now we're going to go down to chains that have 5 carbons in length with 3 substituents. So we can have 3 substituents, 2 at the earliest position possible, and then the other leftover one at the third position. So this would be called 2, 2, 3 trimethyl, because there's 3 of them. Tri is 3. Methyl is because they're all methane groups, but they're substituents, so they become YL. And then the longest chain is 5, so you say pentane. Okay, and then you can have 2, 2, 4. 1, 2, 3, 4, 5. Here's your 2, 2, and there's your 4. So that would be 2, 2, 4 trimethyl pentane. Can't go to 2, 2, 5 because that would extend it back to a hexane. So that closes off that possibility. But we can have 2, 3, 3. 1, 2, 3, 4, 5. 1 at the second position, 2 at the third position, so that would be 2, 3, 3. Trimethyl pentane. My guess is all these molecules have very similar properties. They're probably pretty close in melting points and boiling points as well, but there would be some slight differences. Minor differences, but they would be detectable in my opinion. I don't know what they actually are. 15. 1, 2, 3, 4, 5. You could also separate all of them, have 2, 3, 4. So you'd say 2, 3, 4 trimethyl pentane. The 16th possibility is 1, 2, 3, 4, 5. 1 at the methyl group at the second position, and then an ethyl group right in the middle. So that doesn't extend the chain, doesn't make it any longer. You still get 1, 2, 3, 4, 5 as the longest chain. So you don't change the name. It's just going to be I forgot to alphabetize in my answer. So it's 3-ethyl, 2-methyl, because E comes before M. Pentane. Put dashes after the numbers leading to the word. 17th possibility is 3-ethyl, 3-methyl. 1, 2, 3, 4, 5. So you have the ethyl group here, and also the methyl group. So you 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the longest continuous chain is 5. That's the third position. So you'd say 3-ethyl, 3-methyl pentane. That's up to number 17. And there's actually one more. It's a butane. So let me just harass that for you. And you get 1, 2, 3, 4. That's going to be the longest chain, but now you have 4 more carbons to get rid of. So you're going to put 2 on the second position, and 2 on the third position. That's going to be called 2233 tetra, because there's 4 of them, methyl butane. There's actually another name for that. It's called isooctane. This is the octane you find in fuel. They highly branch it because it burns more gently. It burns, normally when your engine is running, the pistons are going up and down about 50 times a second if the engine's turning at 30 RPM. So you're getting, in a 4-stroke engine, you're getting those pistons having an injection of fuel. Out of those 3,000 times a minute, they're getting 1,500 squirts of fuel. So you do the math, 1 second, 1,500 squirts of fuel divided 60 seconds, no sorry. So you get 1/25 of the second for that fuel to explode and push the piston down. So they have to time the chemistry of the explosion in such a way that it's not too violent, because if it explodes too violent, then the piston gets jarred and it actually is hard on the engine. You want it to extend that explosive power over the course of that 1/25 of a second in such manner that you extract the most amount of mechanical energy. And that's the whole thrust of the petrochemical industry, is to create the best explosion inside your engine. And they found that this isooctane is probably close to the ideal for normal engines. Then of course you get high performance engines where the pistons are moving faster, so they get a fuel that has a more rapid explosion, or in some cases they get a fuel that has a slower explosion, because if it explodes too quickly, then you get knocking and pinging because it explodes before the spark plug actually gets does its spark. So there's it's a tricky thing, and there's a lot of tweaking, in the good sense, that is involved in making sure that the engine runs properly. Okay. So I'll continue my notes from the point where I left off there. It says alkanes burn readily to release energy, making them ideal fuel. So our whole society runs on petrochemicals. We make plastics with them. We run all our engines with them. So it's a huge industry. There's a massive amount of money behind it, and the industry really depends on us to continue burning fuel. Although there is a trend now to switch over to making vehicles that are electric, but okay, electric vehicles. Who's charging the batteries? The power grid. How's the power grid generating electricity? In some cases, what are they doing? They're burning fuel. So I don't know. It's kind of give me 6 of this or a half dozen of the other. You're still burning petrochemicals to release energy. If under some kind of idyllic world there was only geothermal and hydroelectric and wind and wave energy, we could probably get away with burning 0 fuels, but we're not there yet. And I forgot to mention solar. You know, I guess if you could imagine the whole Sahara Desert blanketed in electrical, in the solar panels, and then that electricity being equitably distributed over the whole planet, or all the other deserts, you know, covered in solar panels, because you can't really use them for anything else anyway. That would solve our energy problems. But yeah, that's a bit of a dream at the time, for the time being. It's a nice dream though. When you balance combustion equations, I've taught you a million times. If you're my students, you do it alphabetically. Let me give you one example. I don't want to belabor this because you're grade 12s, you should know this by now. But in case you haven't, if you somehow escaped learning this, balance the combustion of balance the combustion of, let's say, butane. Okay, so butane is C4 H10. Obviously, when you're burning something, you need oxygen, and after you burn it, if it's a hydrocarbon and you burned it completely, you're only going to get CO2 and water. There's a simple way to balance any combustion equation, completely foolproof. You never get it wrong. You do it alphabetically. First the C's, then the H's, then the O's. C, H, O, in the same order as the letters appear in the alphabet. Okay? So just do this mechanically. There's 4 C's on the left. There's got to be 4 C's on the right. So put a 4 over here in front of the CO2. Never mind about the oxygen. Then you look at H. There's 10 H's on the left. You got to have 10 H's on the right. So you're going to put a 5 in front of H2O. Again, never mind the oxygens right now. Then you look at the oxygens. Okay? But when you balance the oxygens, you look at the right side first. Count up how many oxygens you have. You got 4 by 2 over here. There's 8. And 5 times 1 over here. There's 5. That means you got 13 oxygens on the right. You got to have 13 oxygens on the left. So put a 13 in front of O2. Oops, you got twice as many as you need. So put a 2 under the 13 and it halves it. There's your balanced equation. It's balanced out. If you don't like fractions, just double everything. You get 2, you get 13, you get 8, and you get 10, and now it's balanced using only whole numbers. You'll notice that when you have alkanes with an even number of carbons in them, you always get that fraction. If you have an alkane with an odd number, it works out perfectly. Okay, so I have a million videos on this. Just look at the balancing playlist and you'll find it if you still don't get it. So that's how you balance the combustion of alkanes. Now let's look at the next kind of alkane. Actually, it's alkene. So alkenes are hydrocarbons that contain a double bond. Their suffix is -ene. It ends in -ene. Let me just check for time. How much we got up here? 22 minutes. I'll give you 8 more minutes. Hydrocarbons with a double bond are called alkenes. And their suffix is -ene, obviously, so here's an example. 3 carbons with a double bond between 2 of them. You're going to number from the side that gives the lowest number to the alkene. So you're going to call this prop, because there's 3 of them, and end it in -ene. So it's propene. You can put 1 to show that the double bond is at the first position. Not really necessary, because the only place you can put it is the first position. If I was to put it on this side, it's still called 1-propene, because then you would number it this way instead. Okay? That's how it works. If I have 4 carbons in a row, but with a double bond in the middle, now it creates a situation where, because this double bond locks the carbon atoms, doesn't allow them to rotate anymore, you can either lock the methyl groups on opposite sides, or you can lock them on the same side. So you can get this, or you can get that. If you get this, it's called trans. If you get this, it's called cis. If they're on the same side, they're called cis. If they're on opposite sides, they're called trans. So if they're trans, meaning they're on opposite sides, and of course the double bond is at the second position, so you call it a trans 2-butene, because there's a double bond, and this would be called cis 2-butene. The metric system now, they've come up with a German naming system. If they're both on the same side, it's called E. No, sorry, if they're on opposite sides, it's called E2-butene. And if they're on the same side, if they're together, they're called Z2-butene. The way you remember this one is you think of the word for the word in German for together is zusammen. So think of a German guy saying, "Let's go out on a date." Together. He says it with a German accent. Together, Z. Okay? Z2-butene. That's how you'll remember it. Sorry to my German watchers. Double bonds. Do not rotate. Which geometry of the molecule. So that's why you get geometric isomerism. And trans and cis molecules will have the same formula, but they have different chemical properties. You've heard of trans fats, which are supposedly bad because they tend to gum up your digestive enzymes. They don't get digested well. So they're added to food to increase their shelf life because even the germs don't like it. So the food doesn't tend to spoil as well. But would you eat something that even the germs don't want to eat? I wouldn't. So that's why they say don't include trans fat in your diet because it tends to be bad for your health over the long run. Let's do one example and then we'll break for the day, and then I can give you just a little bit of organic chemistry examples tomorrow, and maybe I'll show the pictures of it in my notes because there's lots of notes and we just don't have time to go through all this, so I'm going to have to limit myself to teaching you a little bit of nomenclature. Here we go. Here's the question. So just to recap, when the two heaviest substituents are on the same side of a non-rotating double bond, it's called cis. If the two heaviest substituents on the molecule are on opposite sides, the molecule is called trans. Okay. So this is the practice example on page 1076 of your book, and the question is, what are the straight chain isomers of C6H12? So normally the formula for an alkane with 6 carbons is C6H14, but because it's a double bond, the molecule is going to be missing 2 hydrogens because those 2 bonds are going to form the second connection between the carbon atoms. So whenever you see unsaturation, if 2 hydrogens are missing, you know there's 1 double bond. If 4 hydrogens are missing, then you know you have 2 double bonds. And if you get an unsaturation of, say, 8 hydrogens, then you know that you've got a benzene ring probably, because with 8 hydrogens, not only do you have 3 double bonds, you also have a ring, and rings also take away 2 hydrogens. So anyway, let's look at this. The answer for this question would be 1, 2, 3, 4, 5, 6. There's a straight chain. You can put the double bond right on the end. That would be called 1-hexene. You don't even have to put the 1 really, because if you just say hexene, people will realize that because you haven't put the number, it's got to be in the first position. Then you can swing that bond to the second position. And by the way, it doesn't matter where I can put it here or I could put it on top. It still symbolizes the same thing. There's a double bond. That's what I like about things when they're simple. Trans to hexene. Okay, why did I call it trans? Because one end is down, the other one is up. They're on opposite ends. So it's trans, or you could say E to hexene. Either way. Now we can have the other possibility, of course, where we put the things on the same side. Then it's called cis to hexene. You notice I've already contracted the trans to just T. Any chemist will know T stands for trans and C stands for cis. So cis to hexene. And then I can put it to the third position. 1, 2, 3, 4, 5, 6. And I put the double bond at the third. Oh, wait a second. 1, 2, 3, 4, 5, 6. Yeah. 1, 2, 3, third position. Put it there. They're on opposite ends, so that's trans 3-hexene. And of course, if you have a trans, you got to have a cis. So let's do it like that. This is called cis 3-hexene. And that's it. Okay. Tomorrow I'll talk to you about alkynes. You can watch a little bit of my nomenclature playlist. I really don't have much of a playlist when it comes to organic chemistry. That's the one last thing I have to still build up on my site, and I am working on the notes on it, so eventually I will have something. All right, so we'll see you tomorrow, where we are going to talk about the reactions of alkenes and alkynes.